Welcome to ACI, the Network Made Simple learning series. In this video, we will cover Module 3, Configuring Logical Connectivity, Chapter 2, Part 2, Putting it all together, behind the scenes. After successfully finishing our configuration, let's get a high-level overview of what ACI did behind the scenes and a few tips on how to verify packet forwarding for troubleshooting purposes. First of all, when we assigned the web server VM to the EPG, the first thing the VM did was to ARP for its default gateway, just like any regular host would do. This triggered an ARP request within the VRF and bridge domain for that EPG. The ARP request made it to the ACI leaf, in this case leaf 102, and leaf 102 did two things initially. First, it stored the IP and MAC address information as well as the interface where the endpoint was learned from in its endpoint table. In ACI, we use the endpoint table instead of using a MAC address and ARP table. And two, this new entry was reported to the spine layer using a protocol called COOP, which is running automatically between spines and leaves and which allows the spine layer to have a full directory of endpoints and their VTEP sources as they connect to the ACI fabric. As you would imagine, this communication is happening over the overlay 1 VRF within the infra tenant, and the spines receive this information through their automatically assigned Anycast TEP IP address. The same process will repeat for every endpoint you connect to ACI, which is exactly what happened with the DBVM and the new web server VM, making the process and scalability very efficient, since only local entries are stored on each leaf and remote entries will be learned and installed in the cache only if required. Keep in mind that ACI uses a conversational learning approach for many things, including VRFs and bridge domains. Therefore, only those resources used in a specific leaf will appear as part of the active configuration. All local traffic running within the same leaf switch will flow pretty much as a regular switch, forwarding traffic to the corresponding port. We can verify this by issuing the show endpoint command at the leaf level, where you can see that all local entries are displayed with an L letter. With this command, we can clearly see the interface every endpoint has been learned from. ACI leaves learn IP and/or MAC addresses, as we mentioned before. Therefore, if both are learned, you will have a /32 entry for the IP address, or even a /128 if you're using IPv6, and a separate entry for the MAC address. If you do not want the ACI fabric to learn IP information, you can disable unicast routing in your bridge domain, but keep in mind that you need unicast routing enabled if you use bridge domain subnets for things like Anycast gateway. Then, if an endpoint like the new web server VM tries to establish communication with an endpoint that is not present in the leaf local endpoint table, for example, the DV server, the leaf receiving the request will ask the spine layer about it. This process is known as a spine proxy. The spine layer will then perform a lookup for the requested endpoint in its COOP table. You can take a look at it if you issue the command show COOP internal info IPDB on any spine switch, where you will be able to see all the info regarding every endpoint, including the VRF, VXlan network identifier, and more. If we take a closer look at one of these entries, we can see that there is a tunnel IP address for each one of them. We can match that tunnel IP address with the corresponding leaf performing as VTEP by issuing the command ACI diag-FMB read. With this info, the spine will now send the next hop VTEP information to the leaf that requested it, and the leaf will show this newly learned entry with an O tag, indicating it is a remote entry within its endpoint table. Once that is done, traffic will flow on top of a corresponding VXLAN tunnel over the ISIS underlay using ECMP in order to leverage all connections. If we now take a look at leaf 101, the same process has already happened, and we can see multiple entries with an O tag pointing to tunnel 37 as the next hop. If we issue the command show interface tunnel 37 now, we can also see the VTEP destination IP address there, which will point out to leaf 102 once we issue the command ACI diag-FMB read, as we learned before. Remember that as traffic enters the fabric, leaves will automatically add a VXLAN header to the original packet, which includes the corresponding tenant, EPG, and bridge domain information as part of the VINIT and VRF values, amongst others. Now, if we go back to the bridge domain options, specifically in terms of flooding, we have a couple of them that are important for you to know since they affect how endpoints are being learned. The first one is when ARP and non-unicast flooding are set to off, and the destination endpoint information is not in the spine scope database. In this case, the spine layer will drop layer 2 traffic and perform something called Arp Cleaning for layer 3 traffic. Arp Cleaning means that the spine will check the requested endpoint IP against the configured bridge domain subnets and send a clean packet to each leaf with those configured subnets in order to generate ARP flooding locally. This is useful when you have silent hosts. However, keep in mind that you must have the corresponding subnet configured within the bridge domain, and IP routing must be enabled in order for this to work. With this configuration, ACI optimizes forwarding and flooding behavior by leveraging spine proxy. Now, the second scenario is when ARP and non-unicast flooding are enabled. In this case, if the destination endpoint information is not in the local endpoint table, the leaf won't reach out to the spine layer as we learned through the spine proxy. Instead, it will send a directed multicast flood where the destination multicast address will be one of the automatically assigned ones to each bridge domain from the GPO address pool that we created as part of the initial APIC setup wizard, as you may remember, and which both leaves and spines are subscribed to. If you want to verify the automatically assigned multicast address for each bridge domain, just go to the bridge domain and hit on the Advanced tab. You can issue the show endpoint command both at the leaf level, as we have learned, and at the APIC level in case you want to see all the endpoints that are currently in your ACI fabric. One important consideration for the output of this command at the leaf level is that there is a VLAN/domain header column, as you can see, and the VLAN that appears there is different than the encapsulation VLAN. If you remember, our VLAN pools go from 2110 to 2130 for VMware and 2143 for our Nexus 5K connection. This may throw you off for a second, but the reason behind this is that ACI leaves use internal VLANs for some functions like SVIs and pervasive gateways. These VLANs are known as platform-independent VLANs or PI VLANs, and they are locally significant to each leaf. As you may remember, ACI uses external or encapsulation VLANs to classify traffic as it comes into the ACI fabric, and these are logically significant between the port and the endpoint. This means that the same encapsulation VLAN ID could be used for different EPGs and even different tenants on different ports. Therefore, ACI uses the PI VLAN as an internal method of communication for some functions in order to normalize layer 2 communications at the leaf level. I won't cover PI VLANs in this chapter, but you shouldn't have to deal with them for troubleshooting purposes. Therefore, you want to make sure that you look at the encapsulation VLAN column most of the time. Before, in legacy switches, we used to type the show VLAN command to see the VLANs on a switch. In ACI, I recommend you don't use this command since it will show you the PI VLANs list, which may not tell you much. If you want to see the encapsulation VLANs at the leaf level, use either the show endpoint command or the show VLAN extended command, which will show you both the PI and the encapsulation VLAN association list. Finally, how does ACI handle VM mobility? Well, if a VM moves due to vMotion or other functions, the leaf where this EP moved to will learn the endpoint entry and will send the registration to the spine through COOP, as you have learned. Then, the spine will compare this new entry with the older one learned from the previous leaf, understanding that this endpoint moved. Therefore, the spine layer will not only update the entry in its COOP database, but it will also update the leaf that previously had this endpoint with something called a bounce entry. Bounce entries are tagged with a B in the endpoint table. This way, ACI automatically ensures that both policy enforcement and traffic forwarding are always consistent and correct. As you can see, there are lots of things happening behind the scenes that are fully automated for you, and you will hardly have to get this deep as part of your daily operations. However, if you feel interested in learning all these even in further detail, here are a few sessions and certifications that can get you started in that direction. As a summary, ACI is fully automating your VXlan forwarding and policy enforcement with a few differences compared to regular networks. For example, leaves use endpoint tables as substitute for MAC and ARP tables. ACI uses COOP to keep endpoint registry updated, and local traffic switching follows the traditional forwarding model, while remote traffic is automatically encapsulated using VXlan. Keep in mind that if an endpoint entry is not found in the endpoint table, the leaf will then look for it in its routing table when all 3 outs are defined, which is exactly what we will cover in the next chapter.
ACI provides you with a better, simpler, and secure network, any size, anywhere, and on any cloud. If you want to learn more about other common tasks and how ACI radically simplifies network provisioning and operations, please watch the rest of the videos in this series. Thanks for watching.